So for today you wrote some papers, right? And then you had to do the Bible homework. Just make sure I'm on the same page with what we need to cover today. All right, so due for today was all three of these were papers, right? And then three, so this was what, SQL, this was Python 2 versus Python 3, and what was the last one? History of programming languages and where Python fits in. Okay, got it. And let's see what we're doing for hello world, blah, 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 okay. That's drill 3, 4.
They do by class time, right?
Yes, by 6 p.m.
Because I saw there's like 3 that were at 10 a.m.
Are you lying?
No, like the drill and the projects.
No, it should have been by class time. The ones for this week or like a future one?
All of them.
Really? No, I'll double check. They're due by class time. I'll update the times on them. Enter number. Okay, got it. And then the project for next week is okay, got it. All right. So let's keep trucking here with what we were talking about from last class. So, if we just flip through here real quick, just so since it was all done in one class. Talked about the history of our operating systems on the Windows side, on the Mac side. We talked about that story, Microsoft and Apple, and how those guys came together, split apart, and now they're back together. And we talked about Next computers, right? So where Apple kind of came from, what actually is an operating system. It's the kernel, not the distribution that we call Windows and Mac OS today, or the version of Linux. That we'll use in here is Raspbian, or you can use Ubuntu. So we talked about Linux some. So this is the same one Raspberry Pi uses. It's a pretty lightweight, doesn't use a lot of system resources. So if you were to run that locally on your machine, you might be able to get by. Otherwise, just delete some of your crap. Maybe put that on an external jump drive instead of having it all locally there. But whatever you want to do. So then, or you can use Ubuntu. Here's some other distributions, let's say. But Ubuntu would be my preferred Linux distribution. Raspbian would be if you need a lightweight one. I'll actually show examples with Raspbian in here because it typically runs better in a virtual machine. So we talked about virtual machines last time, how they work. Mentioned the programming is the skill, language doesn't matter. So just because we're using Python in here as our example language really has nothing to do with what we're learning in the class. We're not learning Python, we're learning to program. How do human beings solve problems? Memory, asking questions, and repetition. 100% of programming languages have facilities for these three things. We accomplish this through variables, conditionals, and loops and functions. So today we're going to start focusing on how those things come together in Python, and you can apply those exact same things to other languages. Talked about why programming is hard. Human beings are so good at it that we have trouble articulating how we do it. We had this picture here showing kind of the history of our programming languages. We started talking about, we talked about web languages for a while, right? Yeah, here's our web server stuff. We talked about APIs, data representation languages, XML, JSON. Okay. So we started talking about C. So C was a procedural programming language prior to object-oriented programming languages. Back in this picture here, we have C as procedural, C++ and Objective-C are both object-oriented. This was the direction Microsoft went when we went object-oriented. So this is Microsoft right here. And over here we have Apple, mostly because they hated Microsoft and weren't going to use the same language, but both of those are effectively object-oriented versions of C. We talked about object-oriented telephone versus procedural telephone, pile of wires versus the thing that actually physically looks like a phone. What did C++ do? It allowed bad programmers to make poor choices. So the example would be if you're inviting me to your party, you could, C++ would allow you to hand me the house instead of the address where the house is found. So that's kind of a big deal. We talked about pointers and how memory actually works and how computer scientists initially, especially beginning computer programmers, are often intimidated by base 16 hexadecimal numbers. They represent addresses and inside of our computers. The reality is that memory or addresses inside of computers are simple compared to our addresses in real life. In computers, everything is on, all the houses are on one big long street. All right. Whereas with human addresses, we have a street number, we have a house number, we have a city, a town, a state, all this stuff that adds up to where can I find a particular thing. So human beings are typically intimidated by computing type addresses because they look scary, even though they're far simpler than the addresses we use in real life. Where does Java come in? Java is a platform-independent language, which means you write it once, it runs anywhere. So it runs on any platform that supports the Java virtual machine. So back Sun Microsystems was the maker of Java. They created this program called the Java Virtual Machine, which is, remember earlier in last week's lecture, we talked about virtual machines in and of themselves, which would be a computer running in software, right? So the Java Virtual Machine is a computer that knows how to run Java programs. So that's the Java virtual machine. And what they did is they wrote it for Windows, they wrote it for Mac, they wrote it for Linux. So they ported the Java virtual machine to all sorts of different platforms so that all of those different platforms could run Java programs. You only had to write your Java program once and it would run on all those other machines. Microsoft, big lawsuit, stole Java, got sued, lost the lawsuit, came out with C#. C#, the funny joke is it's also platform independent. It'll run on any platform as long as it's Windows. So make sure you choose the platform that is Windows and then it will run on any platform. But basically C# and Java, roughly the same language. We talked about the web server stuff. How does the internet work? How do APIs work? We talked about RESTful APIs being built on top of old school hypertext transport protocol, HTTP. Data representation languages, Java, or JSON rather. HTML being an example of a data representation language. Node.js being from our chart up here. These are kind of the history of our web languages where Node.js allows us to bring the front-end languages that the front-end developers are often working with, that is the JavaScript, HTML, CSS, JavaScript, and if you're a back-end developer, it allows you to use that same JavaScript to write code on both the front and the back end. Even though we're arguing that programming is the skill, the language doesn't matter. If you're somebody who picked up computer programming as a profession and you don't necessarily have the foundation that we're trying to build behind that, then going and learning a new language might be trickier. So if you're already familiar with JavaScript and you can use that exact same syntax to work on the back end stuff, there's an advantage to that. Okay, so this is kind of where we ended off here. Let's start talking about CPUs a bit. What is the CPU? What's the processor? What does it do? What's its job? How does it work? Okay, does calculations and stuff. Okay. So mathy stuff, anything else that it might do? What's it capable of doing? Maybe the generic thing might be it's capable of all things that are generic to computing, something like that. I like to think of the CPU as a collection of magic tricks. So if you were to look at the blueprint of your CPU, inside of that, what you'll see is a whole bunch of little tiny computer programs written in hardware. So created out of wires and logic gates, ands and ors and things like this. But each one solves a little tiny problem. All right, so it's a collection of magic tricks where each trick solves some very small problem. Now, a trick in and of itself might not solve a very meaningful problem alone. But if I do this trick followed by this trick, followed by this trick, followed by this trick, and you do that 50 times in a row, you may have actually solved a real thing. That make sense? So the job of the CPU is to provide a collection of tiny solutions that can be joined together to solve larger / more complex problems. All right? That's what the CPU is. As computer programmers, it's our job to tell that guy what to do. Right? Ultimately, it's do trick 1, trick 17, trick 24, and trick 38, and boom, something has happened. Hello world is printed on the screen, something like that. All right? Now, there are 3 kinds of programming languages: machine, low level, and high level. What language do computers speak? It's not a trick question. Zeros and ones, right? Yeah, binary. Binary. Zeros and ones. That's the language of the computer. Now, if I handed out everybody the little 2-button keyboard and said, go to work, how many of you would stay programmers after that? Just tapping out programs all day long, 0, 0, 0, 0, 1, 1, 1, 0, 0, 0, blah, 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 blah. We'd make mistakes left and right, correct? Not for human consumption. Zeros and ones are not our cup of tea. Computers love it, and we're okay with that because we're the boss, right? But ideally, we want to have a tool that allows us to tell this guy what to do, ultimately tell the CPU what to do, in a way that allows us to still maintain our humanity, still solve problems the way we already solve them as people. But this guy still gets to still gets his instructions in zeros and ones. Somebody has to do the translation between us and the zeros and ones, and we all just agree we don't want the 2-button keyboard. All right, so machine language, that's our binary zeros and ones. A low-level language has a one-to-one relationship with the CPU. And what do I mean by that? It's every line of code we write is equivalent to a single magic trick on the CPU. So the CPU has this collection of things it knows how to do, right? And whenever we write one line of low-level code, it's equal to one of those instructions. Still pretty tedious because we just used the example that we might have to string together 30, 40, 50 of those magic tricks in a row to accomplish something amazing, right? High-level language has a one-to-many relationship with the CPU. Every line of code we write is equivalent to a bunch of magic tricks on the CPU. Make sense? All right, so we would call that maybe a power tool. If we had our druthers as programmers, we want to spend a high percentage of our time right there. We want to be speaking in a as English-like way as possible, as human of a way as possible, and have something else convert that into the zeros and ones. Maybe taking a quick little pit stop at this low-level language in the middle. Make sense? All right, so how many of you have heard of something called a compiler? Okay, so we compile programming languages. Python here, actually I'm just going to quickly insert an extra slide in here just to keep the confusion rolling with these slides that say 3 types of languages, 3 types of languages. We'll throw one more in here. That is, there are 2 types of programming languages. Remember, all these slides are kind of looking at languages through different lenses, different angles. Okay, 2 different kinds of programming languages. We have interpreted languages, and we have compiled languages. All right, I'll actually go ahead and even give ourselves another slide. There are 2 types of programming languages. We have loosely typed, and we have strongly typed. Now again, all this stuff goes hand in hand with us looking at this picture, and whenever we're using a computer programming language, we kind of want to know, where does this language fit in the ecosystem? What kind of language is it? Because that gives us some information about how we might use it. Or when we're out in industry and we're trying to solve a problem, and we kind of understand the requirements of the problem, we might decide what is the best tool to use for this language. Now, if you're doing some webby stuff, PHP was a language specifically designed for the internet, for the web. So you might lean towards one of those languages that already has a bunch of web built-in stuff in it to allow you to solve those problems, as opposed to if you're writing a video game, you might tend towards something like a C++. If it's got to be a high-speed video game for like a PlayStation or something like that, but if it needs to be cross-platform and it's something more like Angry Birds, maybe you look at Java or C#, that type of thing. Okay, so one language isn't inherently better or worse than another. They're all programming languages, but certain languages might lend themselves to a certain kind of problem more so than another language might. All right, so understanding where our various languages fit in the world of languages can be helpful. All right, so 2 types of programming languages, loosely typed versus strongly typed, and we're going to swing back to that here in a few minutes. But for right now, we want to look at this interpreted versus compiled. So interpreted languages use a interpreter to convert high-level language to, I'm just going to say machine language, during, we're going to put that in caps, during runtime. Whereas compiled languages use a compiler to convert high-level language to low-level language prior to runtime. And we're going to say ultimately to machine language using something called a linker. So kind of a compiler works hand in hand with a linker to ultimately get you an executable. All right, we'll explode that here a little bit. All right, so 2 kinds of broad classifications of languages. We have interpreted languages and we have compiled languages. Now we're just gonna make a connection here. All the languages over here are interpreted languages. All the languages over here are compiled languages. One's not better or worse than the other. Okay, we're going to talk about the differences between these, but we're seeing now a broad classification between these two sides of languages, right? So we have everything to the left here is interpreted, everything to the right is compiled. Let's deal with this slide. Two types of programming languages, loosely typed versus strongly typed. Loosely typed languages, this all deals with variables. Do not require us to associate a type of value that a variable is built to hold. Whereas strongly typed languages do require us to associate a type of value that a variable is built to hold. All right, this is a syntax thing where if I'm in a language like Java or C++ or C, I would say like int a equals 5. I had to define that that variable a is built for holding integers, and that has meaning to it. All right, we're going to come back to this. Whereas in a language like Python, I can just say a equals 5. All right, so loosely typed, for example, I can say a is equal to 5. And then we would say at runtime, a type inference engine figures out what kind of value is in A, so it can determine if, well, let's see, what kinds of things we can use it for. Strongly typed language, we'd have to say something like int a equals 5. And then this would be prior to runtime. We know that a is built for holding integers, i.e., you can do math and stuff like that with it. We know beforehand the kinds of things we can use that value for. That make sense? Going back up to this picture. All these languages over here, loosely typed. All these languages over here, strongly typed. So, not that it absolutely 100% has to be this way. They are separate arguments, but interpreted languages tend to be loosely typed languages. Compiled languages tend to be strongly typed languages. Those two approaches tend to go hand in hand. All right? And why? Why is that a truth? Loosely typed tend to also be interpreted. Strongly typed tend to also be compiled. Now, we would say under loosely typed, these guys are relatively slow. Whereas strongly typed, these would be relatively fast. Now, human beings, we might say that, oh, faster is always better, right? So if you're writing a video game or an operating system, something like that, you're probably going to choose something like a C or a C++, one of these strongly typed, compiled programming languages that are relatively fast. As opposed to if you're doing something like web, where it doesn't need to have, you don't measure a web page, the presentation of a web page in like numbers of frames per second. Or you don't think about Microsoft Word or something like that. You're not thinking about it in terms of performance. You're not going out and getting a better graphics card to drive your web browser, right? You're getting a better graphics card to drive your video games. So the idea here is it's not that loosely typed interpreted languages are worse. They're typically used to solve different kinds of problems where absolute maximum speed is not a requirement. And that's okay, because our computers are really fast, right? For a lot of applications, if you wrote a C program, which we're going to say is really, really, really fast, and you compared it to a Python program, which we're going to say is really, really, really slow comparatively, it's like me versus Usain Bolt in a race. It's probably actually worse than that. Python is probably slower than C than I am compared to Usain Bolt. Everybody know Usain Bolt? Super fast runner guy? Definitely faster than me. You don't know my foot speed, but we can at least make we can make a pretty strong guess that he's faster than me. I have burst speed. I'm good for about 6 feet. Then I'm done. That's it. That's all she wrote. I got to slow down. That usually involves falling over and rolling a little bit and know thy truth, right? All right. So we can say that Python is really slow compared to C. But we all know, especially now that you've done these papers, Python's a really popular language, isn't it? Several of these other languages are popular too, but Python is almost like, when you look at modern trends, data science, machine learning, things like that, Python seems to be like this go-to move these days for getting into those things. Why is that?
Simple, easy syntax.
Okay.
Code depends on readability.
I'm not sure it's not. You could probably reasonably make that argument. My opinion is it would be difficult to defend that it's that much easier to read, that the syntax is really any more simple. In fact, I might even argue that Python is tougher for beginning programmers to first work with because it forces indentation. And my experience in working with beginning computer programmers is they hate to indent. They hate to make their code look good because so much stuff is like they copied and pasted in there. They don't know why it doesn't work. And that indentation rule with Python is just one more thing to break. Now, as a teacher, I love it because if they learn Python first, then when they start going and doing other languages, they're already used to making their code look organized. They're used to indenting, even though it's no longer actually required. I just don't necessarily tell them that, right? You know, the opening colors and curly braces in C, C++, C is perfectly happy with you putting the entire program on one line. It doesn't care. So we could say Python, I've heard this argument, Python's an easier language. I don't really think that's the truth. Why else do you think Python is popular today? I think it's pretty related to what we've been talking about the last several minutes. Do you think it is easier to take a language like Python and adapt it to things like machine learning or data science than it would be to take a compiled language like C or C++ and recreate it for specialized tasks like that? We got to think about how does a compiler versus an interpreter work? So when you have a compiled language, it takes your C or C++ code and it has to magically turn that from this high-level one-to-many relationship with the CPU into effectively zeros and ones with a pit stop in the middle of low-level code. That's difficult. Let me put something here. Compiler so this guy translates high-level code to low-level code. All right. Now, we're going to say better compilers make better, i.e., more efficient, low-level code. We might even say that the job of a compiler is to make a bad programmer look better. So if you were to look at a bad programmer's code at the assembly level, at the low-level code level, they might not look dissimilar to a good programmer's code at the low level. Because you're looking, so if I write a C++ program and you write a C++ program, doesn't matter how good or bad either one of them is, in the end, they might look very similar at the low level. That compiler has made us both look good, even though one of us might not be. Make sense? That's the job of a compiler. And compilers are really, really complex. They're difficult things to write. I want to kind of show that by an example. How many of you in here have ever worked with assembly language, a low-level programming language? All right, so actually let's put it on this guy. When we compile code, we target both an architecture as well as an operating system. So we're starting to connect some of our dots from last week, right? All right, what's an architecture? So when I talk about a computer architecture, what am I talking about? Okay, it's hardware, specifically what kind of hardware? CPU hardware. So we're usually talking about something like whether it's the i386 architecture, which would be like an old Intel compatible architecture, PowerPC architecture, MIPS is another architecture. Okay, so each of these have their own assembly language for them. So an Intel-based processor has a set of magic tricks that it knows how to do. And a PowerPC processor has a set of magic tricks that it knows how to do. Now, they might have a different take. In fact, they would. PowerPC is what's called a reduced instruction set CPU. So it actually has a smaller number of magic tricks, hopefully with which you can accomplish the same kinds of tasks. Didn't work out so well for them, whereas i386 is going to have a larger collection of magic tricks. So the idea is Intel has said, we think you can solve all of the world's general computing problems today with this set of 5,000 magic tricks. Just pulling a number out of the sky, all right? So whenever you write code in a high level, that compiler is going to translate your code into those to a collection of those 5,000 magic tricks. Now, if we roll back 20 years into an earlier Intel-based processor, which was also the i386 architecture. Before this, we had the 286 architecture. Before that, we had the x86 architecture. All of our processors today are supersets of that. So how many of you have ever gone out and bought a piece of software for your computer, and on the side of it, it has minimum system requirements? It might say Windows 95, and it might say Pentium 2 processor, 233 megahertz, something like that. Even in a modern piece of software, the side of the box, assuming boxes still exist anymore, might say something that's pretty old, right? Like that. Why do you think that is? That's related to this thing right here, that we're targeting both an architecture and an operating system. So when somebody creates a piece of software, what they're doing is they're saying, okay, we're going to compile this software so it works on Windows 95 or later, as well as a Pentium 2 processor or later. And this is making a big assumption, though. It's making a big assumption that future versions of Windows will be backwards compatible with old versions of Windows. It also makes the assumption that future versions of Intel processors will be backwards compatible with old versions of Intel processors. So when they say the minimum operating system requirement is Windows 95, what they're basically saying is, you know what, we might use something that Windows 95 provides that Windows 3.1 did not. Therefore, if you try to use an older operating system, it's not going to work because we've made the assumption that a certain thing is present. Make sense? Kind of like magic tricks. They're called system calls. We'll talk about them in a few minutes here. So with that in mind, that's why sometimes you'll even look at modern software and it has like pretty old system requirements. You're like, oh, I'm way faster than that. It probably doesn't necessarily care that much about what your CPU speed is. It cares more about what your CPU architecture is. What magic tricks does your CPU support? Does that make sense? And generally speaking, like this year's Core i7 processor, Intel Core i7 processor, is a superset of last year's Core i7 processor. You know, so if you go out and buy a new computer today, you know, you might get a good deal if you buy last year's 8th generation Core i7 processor running at 2.7 gigahertz. Or you can get this year's 9th generation Core i7 processor running at 2.3 gigahertz. It actually sounds slower. Which do you get and why? Realistically, newer is better, right? That's what they say. All the commercials come out, they say the 9th generation Core i7 processor is up to 50% faster. What does that mean? What does it mean for it to be able to say that it's up to 50% faster? It has to be able to do at least one thing 50% faster. Maybe they've added one magic trick, or maybe they've optimized one of the magic tricks. So for a very, 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 very specific task, under the perfect conditions, that processor is 50% faster. Under every other condition, it's basically the same processor. Make sense? So if you really are doing your shopping, you have to go and find out what's really changed in the architecture since last year and decide, is it going to be something you ever take advantage of? Usually you also have things where they're more energy efficient and things like that. So you have some other perks as well. But, you know, human beings were usually about the speed. 50% faster may not actually benefit you. I'm not saying necessarily don't buy the newest one. Just as technology specialists, we should have open eyes when we buy something, right? Know what we're dealing with. Okay. So, compiler has to target both of these things, an operating system as well as an architecture. So an architecture is effectively what magic tricks do I have to work with? That's what we're really asking. That's what an architecture is. It's the collection of magic tricks that the compiler is allowed to output, right? Because it's taking high-level code like Python or Java or C#, and it's spitting out low-level code. Well, Python's an interpreted language, so it wouldn't be Python going into a compiler, but it's spitting out low-level magic tricks, assembly code, and it needs to know what its target tricks are. Make sense? Similarly, we talked last time about operating systems. Each OS has an API called system calls. So these are the things that the operating system knows how to do. So you might imagine that an operating system is going to know how to write stuff to the screen. It's going to know how to read stuff from a hard drive, write stuff to a hard drive, generalistic things. And all operating systems will do those things. But one operating system to write something to the screen, it might have a syswrite system call, where another one might have an output system call. They both do the same thing. They might accomplish it slightly differently, but they're different calls. They're different magic tricks. So we can think of these as like the magic tricks of the operating system. So kind of like the magic tricks of the OS. Make sense? So when we compile a high-level language, we're targeting both of those things. What's my architecture that this is going to run on top of? And what operating system will this be executed within? And let me show you an example of this. We will use Linux as our example. Read that okay? So this is a assembly language program, so low-level language for the Linux operating system. So it's targeting, this is targeting the x86 processor, so Intel. This is an Intel processor, and this is targeting the Linux kernel. Those two things. That's the architecture, that's the kernel, right? don't worry about this part up here. That's just kind of like the format of the file. This is where the program starts. So we have two different areas here. We have where it starts, and then we have our data section where we remember stuff. So we've defined a couple of variables here. We have a variable called message, and this guy is going to be equal to hello world. And then we have another variable called length, which is equal to the length of message, number of characters in message. All right, so don't worry too much about this. These are just two pieces of information we're remembering. All right, remember all programming languages have facilities for asking questions, memory, and repetition. So here's assembly language showing us how it can do memory. All right, now our program starts. Now inside of our CPUs, we have these little buckets of memory called hardware registers. All right, so EDX, ECX, EBX, EAX, these are all little tiny, think of them as variables made of hardware. It's a really, 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 really fast piece of memory that lives right on the processor. All right, now here's one of our magic tricks that an Intel processor knows how to do. It knows how to move. So when we think about moving things, we probably are moving something from one place to another place. So what are we doing? We are moving the value that is inside of our length. So this is the length of our string hello world. We're moving that into this memory container. Then we're moving the message itself into this memory container. Then we're arbitrarily just moving this number 1 into this memory container. Then we're arbitrarily moving this number 4 into this memory container. All right, so what we're looking at here is how does Intel-based operating systems like Linux actually execute functions. So we want to ultimately print hello world to the screen. That's what we'd like to have happen. And the way we're going to accomplish that is through Linux's syswrite system call. So they have a magic trick in the Linux operating system that some smart person wrote that does a whole bunch of really complex stuff that I promise is way scarier than this, that knows how to write stuff to the screen. All right, so syswrite is like a function, and it requires 3 things to work. It wants to know, what are you writing, how long is it, and where do you want me to write it to? So we've stored inside of EAX the number 4. This corresponds to system call number 4 on Linux, which is syswrite. We have stored inside of EBX number 1, which corresponds to standard output on the Linux operating system. Standard output being the monitor. ECX, we've put our message we're going to write, and EDX is how long it is. All right, because these are the 3 pieces of information that this system call needs. That make sense? So we kind of stage values. We hide them in perfect 4 places. Putting them in those right places is very important in this particular case. So it expected us to put the what do we want to do in EAX, and then the 3 parameters in the correct order in EBX, ECX, EDX. It expected them to be in that order. Okay? So, right here, we are interrupting the CPU and calling upon the operating system to go do its job. So the operating system will right off the bat peek into EAX and say, what is it that you want me to do? You want me to do API system call 4. That's syswrite. Well, if you want me to do that, I'm going to need a couple of things from you. So it's going to go and look in EBX and say, number 1, you want me to write whatever you're going to have me write to standard output. Then it's going to look in ECX and find out, what do you want me to write? The beginning of it. So message is actually something called a pointer to the beginning of that string. And length says, how many bytes do I write? How long do I keep writing bytes for? All right, so that's what this does right here. So now it'll be written to the screen using the magical syswrite system call that has hundreds of lines of assembly code. We're only seeing a simplified version of the assembly code here because this program leverages the underlying operating system. It takes advantage, it's using the operating system as a power tool rather than having all of the logic involving syswrite sitting inside of this file, creating this gigantic, scary thing. We come back to our code here. What do? We move into EAX, a 1. What did we put in EAX before? We put into EAX, what do we want to do? So in this case, we want to do something else. We move into EAX, a 1. We didn't change any of these guys, but that's okay. We didn't have to. Why? Because system call number 1 has to do with sysexit, which requires no parameters. So when we tell the operating system to take over, the operating system will say, oh, well, let's see what you want me to do now. It'll go and look in EAX. It'll say, system call number 1, good old number 1. Kill this program. It doesn't have to go and look in any other buckets or anything. It just says program's done. You've displayed hello world to the screen. Now your program is over. Make sense? That's a low-level program that writes hello world to the screen on Linux using on the Intel architecture, so on an Intel-based CPU, heavily leveraging the Linux operating system. Because this syswrite thing, this line right here, that is kind of like a high-level call, because that one instruction translates into lots and lots and lots of assembly code that syswrite program has in it. All right, so even though we're seeing hello world instead of just being the Python version of hello world being print hello world, we're seeing it be a little bit more complex than that. This doesn't look all that friendly, does it? But we do feel better about this than a wall of zeros and ones. If we had to pick one of the two, we'd rather write this code than a wall of zeros and ones. All right, so given this, we're going to say this is complex enough for us, even though I'm telling you this is actually using Linux as a power tool to accomplish its task. Okay. So our compilers target both an architecture and an operating system. So when we take our input code, Java, C++, C, we then are going to compile it. That is, we're going to translate it from high-level code to low-level code. So from C or C++ into something that looks like this. This is the low-level code. And in order to do that properly, we need to know what architecture are we targeting? So what magic tricks do I have to work with? And what operating system are we targeting? What system calls do I have to work with? Those two things tell me the kind of output I need to create to make an accurate program. Does that make sense? So then I end up with something that looks like this. From there, I would then take this and link it with maybe some other files to create an executable. All right, so we would link it with, they have some other things in here that actually let it run on the operating system, but this gives us effectively a executable file that we can then run directly on Linux and have it spit out hello world to the screen, knowing that this is what's actually driving that. All right? So that's what a compiler does. An interpreter maps a high-level language into equivalent instructions during runtime on a host OS. So for example, Python is an interpreted language. So you write your code in Python, you run it through the Python interpreter, and it takes those commands and turns it into equivalent stuff for that host operating system. The Python interpreter is very likely written in some compiled language. C or C++ or Java or something like that, right? So that these interpreters are actually programs, user-level programs that run on the operating system that instead of making you invent this brand new language, this brand new compiler rather, for Python, or let's say you wanted to invent your own programming language, having to write a compiler that takes all these details into consideration of the operating system and the architecture, and then you need to make it efficient because a baby compiler might be accurate. It might give you accurate output, but might not give you very efficient output. And that's not really a problem for small programs, but maybe for really complex programs that might start becoming a pretty big problem, right? Our computers are fast, but not necessarily that fast for really, really, really complex tasks, right? But we might decide, you know what? We really need a programming language that allows us to conveniently express ideas related to a specific thing. So we were talking about Python. So maybe we're adding stuff to Python for machine learning. Well, rather than creating a brand new programming language that's compiled for machine learning, we could say, you know what? We're going to, and rather than creating a brand new language, even an interpreted language for machine learning, we could say, you know what? A bunch of people already know Python. So we're going to create some library, some extra stuff on top of Python that allow us to leverage something like Python to do machine learning stuff. And all we have to do is teach our interpreter the extra magic tricks it needs to do those things. We don't have to reinvent the language. We don't have to write a brand new compiler. We don't need to do any of those things. So we can accomplish that task. Remember, programming languages are meant to allow human beings to solve problems in a way that's very similar to the way we already solve problems. So with all that in mind, we might say we would rather make a convenience tool by creating a library on top of Python and then have the Python interpreter do the heavy lifting for us, rather than have to invent a brand new language with a compiler for doing something very special. We don't need it to be more efficient. There's already strong C, C++, Java, C# compilers out there that have been gone through iteration after iteration after iteration and produce strong assembly code targeting all the popular architectures, targeting all the popular operating systems. Why redo that work when we can leverage two things? The popularity of a language like Python, the flexibility of any interpreted language to just add stuff onto them, and the speed of our modern computers. We only need to go and consider a new compiled language if our modern computer that we're running the thing on isn't fast enough to make us believe that our interpreted language is fast enough. If I wrote hello world in Python and I wrote hello world in C, now I'm telling you C is the faster language between those two. Do you think a human being would be able to tell the difference? Or is hello world going to pop on the screen just like that? Even though Python is being interpreted and ultimately going through a bunch of hoops and stuff to get hello world out to the screen. What if I were to write a loop that counted from 1 to 1,000? Do you think I'm going to notice the difference between Python and C++? Nope. Computers are really, really, really fast. We have to start solving problems that are disproportionately complex before we actually start noticing the speed benefit of something like C. And really, that's becoming less and less true today. Because now we have these multi-core processors running zillions of gigahertz and all this stuff. Our computers are getting so fast that we really would be hard-pressed to find a true example of a programming language that was noticeably by a human being slower because it was an interpreted language. Dead? Were you just on the very edge of it, or the chair's a danger?
I don't know, I just like this.
This chair just flipped out. Well, I got my entertainment for the night. At least he didn't get hurt, and I would be able to, then it'd be like weird if I was entertained, right? He's laying on the ground crying, and I'm like trying not to laugh, and it would be awkward. All right, so the idea is our computers today are so fast that it's not really a problem for us, right? We just take advantage of how fast they are. These are our slaves, right? They do all the work for us. We tell this guy what to do, and he does it fast, and we don't complain. And realistically, even if something was a little bit slower, let's say you had to run some batch program or something like that that was, going to take 5 minutes in a compiled language. And let's say it takes 6 minutes with Python. Are we really going to care? Probably not. We either are expecting instantaneous output or we're willing to wait for it. Now, if you're doing some sort of scientific research or something like that, and you have a program that might take, a week to finish versus a month to finish, then you might start questioning if you're using the right technology. Make sense? But I mean, we've talked about a huge, gap in possible applications that we're writing there. And where do you think most of our applications fit today? Are most of them that research that might take a week to a month, or are most of them applications that are going to take less than a minute to run? Most of them are going to be that one, right? In fact, most of them are going to be something that takes less than a second to run. So interpreted languages are a very, very, very powerful part of software development today, because we already have established compiled languages that we can apply to those specific types of problems where we do need them to be really, really fast. And if you have a language like C and C++ that has been around for a long, long, long time and been stress tested, and we have compilers that have evolved to write really efficient, low-level code for C and C++, we don't necessarily have a real great motivation to create something else. That's why we haven't had a new compiled language in a while-ish, with one little exception, and we'll finish this up and then take our break. How many of you have heard of Swift? Who makes Swift? Apple. All right, so let's talk about that Swift programming language. So Swift is only like 4 years old or something like that right now. Very young language. Whereas C# came out in 2001, 2002, something like that. Early 2000s, very early 2000s. Possibly even late, 2000s. 2000. Let's just call it 2001. Pretty sure that's when it was. Java, mid-90s. So realistically speaking, we haven't had a new compiled language in 20 years. That's a while. Now, has a lot happened with our computers in the last 20 years that kind of supports what we were just talking about with this interpreted languages, and our computers have gotten really, 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 really fast? And why not just leverage that fact and we'll just write interpreted languages that make our lives easier? Because we can create an interpreted language in a fraction of the time it takes to create a compiled language. By a lot. I teach an undergrad class here, 470, and we're going to have a graduate version of it next year that some of you will, if you go on the computer science track, will end up taking, where we create our own programming language. But it's an interpreted language. You can write a full interpreted language in a semester. Can't so much write a full compiled language in a semester, especially if you want the output to be optimized. You're talking more of maybe years to get something like that. But as human beings, if we're looking for a convenient tool to solve a problem, and we already have strong compilers out there, and we already have fast computers, we could create an interpreted language that has all of the pre-built mechanisms that allow us to solve whatever problem we're solving conveniently. So PHP was kind of specialized for web stuff. Python is now having, kind of gaining its specialization in machine learning and data science, and they'll probably apply it to some other things, but that's really where Python's kind of getting into its own. It's being applied to those things. If we need to do something very specific for a, proprietary type of work at a job or something like that, we could create an interpreted programming language that maps all the little weird things you have to do for that very specific job into a relatively simple programming language. So once the language exists, all you have to do is write the few lines of your made up language code, and behind the scenes, it gets translated into the magic that solves this potentially complex problem, leveraging this really fast computer in the middle. Right? So we haven't had a new compiled language in a long time. Now, the language the Apple people were using, Objective-C, which very few people used for a long time, but something made Objective-C really, really, really popular for a good chunk of time, around 11 years ago. What happened 11 years ago that made Objective-C really popular?
Apple product.
The App Store. Apple App Store. Because first App Store was by Apple, right? The App Store was Apple's App Store. And you had a whole bunch of developers who wanted to go out and make a bunch of money writing apps. Because before that, writing an app and making money off it was not convenient. You had to write your software, then you had to go find a publisher, just like a book, right? That was willing to get it onto the shelves of Best Buy, so somebody might be able to download your software. Okay, now you don't have to put pants on, right? You write your software in grandma's basement, you upload it to the App Store, and they just send you a check. It's great. Apple takes 30%, you keep your 70%, and Apple puts your software in front of zillions of people. It's a great model, right? And people have made lots and lots and lots and lots of money using programming as a skill set for doing this. Well, to write iPhone apps, in the beginning, you used Objective-C. Objective-C was not a popular language before that, but everybody, including myself, went and learned Objective-C to write iPhone apps. About 8 years later, Apple releases Swift. Brand new programming language. Do you think the Objective-C people were complaining? Are Apple users, do they complain about Apple very much? Or are we all just drinking the Kool-Aid? You almost feel a little weird when you go into the Apple store, right? You're just wondering where they keep the special Kool-Aid. It's strange. Apple developed, and I'll tell you what, my research area is in language theory, so I write programming languages. I would say if I had to pick one language as my favorite language that I've ever coded in, it's Objective-C. I just like that language. I think that it's very different than the other ones. The way it expresses itself, I think, is great. It's a fascinating language. I use it with teaching examples, and we'll actually probably look at some examples during this course as we run through a whole bunch of stuff in a very short period of time. But it's one of my favorite languages. Now, having said that, the Apple people were not. The Objective-C developers were not complaining that, it's just been so long since Objective-C got its update and we really need to change. No, they liked the fact that they were the weird ones. Objective-C looks different than other modern languages. It just looks different. It uses these square brackets for syntax instead of dot notation. It's just a strange looking language. Once you get into it, all the components are there just like any other language, so it's not hard to learn. It's just an initial visual thing. Now, who is Apple's number one competitor when it comes to writing software for mobile? Android, right? What language do you write Android apps using? Java. So Android apps are over here. Now, if you look at Objective-C, which I'm telling you is weird, and then you look at Java, and Java looks just like C++, it looks just like C#, so all these languages look basically identical. This guy, you can tell it came from the same grandparent, but it looks different. Let me just show you something here real quick. Let me just give you Objective-C code example. You see the square brackets I'm talking about. Are you serious? Nobody's going to give me a decent Objective-C code example? No, this would be good enough. No, that's not even using the newest stuff. Well, here, I'll just show it to you on a slide. So, Objective-C versus C++. In C++, let's say we wanted to create an object. I'll just use an example. Actually, we'll just do Java here. Java, C++ are the same language, basically. So let's say I wanted to create a random object. That's in Java. The equivalent of that in Objective-C would be random pointer r is equal to square bracket alloc init like that. It takes no parameters. So those two lines accomplish the same thing. Another example might be fraction f is equal to new fraction 1 comma 2. So that's creating the fraction 1/2, for example. The Objective-C version of this would be fraction pointer f is equal to alloc init with numerator 1 and denominator 2, something like that. So you see how it like spells out what the parameters mean? You know, it's just a fun, very verbose way of writing that most of our modern languages have gone away from because they're trying to make the coder type less and less and less and less and less to the point that code is not very well self-documenting anymore. Because you look at code and it's so minimalistic that you really need to have extra comments in there to know what you were doing in some strange places. Having said that, if we go back to our picture here, we said that Android applications are written in Java. And we're saying that the Apple developers are perfectly fine with Objective-C. Swift looks a lot like Java. What's Apple really saying? Hey, Java developers, come over here to the dark side. Write software for iPhone.
It's more flexible, right?
What does that even mean?
I mean, like, you could put like emojis as
Oh, that is true. I'm not calling that flexible. I'm calling it stupid.
Yeah, it's like
Yeah.
a weird way to
Swift officially supports you can name your variables with emojis. Instead of saying, int a equals 7, you can literally say int poop emoji equals 7. That's a thing. That should not be a thing. That should definitely not be a thing. All right. So that gets us through our history of languages. Now, this isn't really a problem. Swift is a perfectly reasonable language, but the only people using Swift today are people writing iPhone applications, which are a lot of people, or people writing Mac applications for the Mac App Store, which is far, far, far less popular than the iPhone App Store. All right, but this brings us up to date with our modern languages, and here we're going to be focusing on Python in the context of generalistic programming. So we'll go ahead and take about a 10-minute break. We'll come back and start chugging along with some Python stuff. Sound good?